All right, this is electrical 2, module 10, circuit breakers and fuses, module number 26210-20. This is out of the 10th edition of the NEC Electrical 2 book, circuit breakers and fuses. So we'll get right into it. Section 1, overcurrent protected devices. So everybody should know by now, overcurrent protected devices. Like these are your two most common. Are going to be your circuit breakers and your fuses. So looking at the trade terms on page 1, circuit breaker is going to be your first one. You should look up different videos on how circuit breakers work, and there's a couple crazier people doing like different tests on circuit breakers and cutting them open, showing them how they work. Pretty useful to know how they work. You got fault current. You should know what that is from the last chapter in grounding and bonding. Fuse, overcurrent protection, pole, short circuit. All these are stuff that you should have heard before and should ring a bell whenever you hear them. But make sure you read back through those trade terms just to have an idea, refresh your mind with what those things are. My first highlight on page 1 is in overcurrent conditions. It's the second sentence in 110. The overload current is an excessive current relative to normal operating current, but one that is confined to normal conductive paths. So this isn't a short, this isn't a ground fault. This is just an overload that's in the normal current path provided by the conductors and the other components and loads of the electrical system. An overload. Next paragraph, first couple sentences are another highlight. Overloads are most often between 1 and 6 times the normal current level. Usually they are caused by harmless temporary surge currents that occur when motors are started up or transformers are energized. So transformers and motors both have a high spike whenever they first start up. And once that initial spike goes away, they get to their normal running, their full load amps or their full load current. Last paragraph on the page, first sentence is highlighted, last full sentence on the page. Continuous overloads can result from motor defects such as worn motor bearings. This is probably one of the most common things that I saw was a bearing going bad in a motor. That's a big deal. I used to have to do thermal checks on bearings for air compressors, big 1,000 horsepower motors. But you're checking those bearings to make sure they're not overloading your circuit. Overloaded equipment or too many loads on one circuit will also cause an overload. Flipping over to page 2, still in that same section, that third paragraph, last paragraph before 120, the first sentence of that's highlighted. The function of a circuit breaker and fuses used in electrical circuits can be compared to that of a pressure relief valve with a steam boiler. So if there's too much pressure or there's too much current, it's going to, a circuit breaker is going to trip, open up the circuit, and no current's going to flow. 120, NEC regulations. So you've got a bunch of bullet points for the different regulations. I've got on the right-hand side of the page, it's the second bullet point on the right-hand side of page 2. First, just the heading is highlighted. NEC section 240.2, underline that, key in on that, has the definition of current limiting overcurrent protective devices. You just pretty much need to know that. Next highlight is the next bullet point down. The whole thing's highlighted. NEC section 240.83C is the interrupting rating. This is important. This is like the maximum amount of rating that any type of overcurrent device can open up. Every circuit breaker having an interrupting rating other than 5,000 amps shall have its interrupting rating as shown in the circuit breaker. So if it's not listed on your breaker, then it is assumed that it is 5,000 amps. The last thing that I have highlighted is the last bullet point on page 2. I just highlighted the heading, NEC section 240.85, applications. So this is where you would find information on circuit breaker applications. That's the end of section 1. Moving on to section 2. Section 2, moving right along. 210, circuit breaker components. So these are the different parts of the circuit breaker. All the way at the top right of page 4, that second sentence all the way at the top right is highlighted. When tripped, the handle jumps to the middle position. So if you're looking up here on the board, you've got, this is your circuit breaker right here. This is your on position. This is your off position. This is when it's tripped. Usually you get a breaker in the trip position because they're testing these on the way out the door. So you physically have to reset it and then turn it back on once you buy a new breaker. And same thing if you have an overload condition with a circuit breaker, it's in the middle position. Then you have to push it to the reset and then back on. Second set of bullet points on page 4, the sentence that's right before them is highlighted. Each group is classified by the largest ampere rating of its range. These groups are. So this is the frame size for circuit breakers. So see if I've got, I don't really show that. So the bullet points that I've highlighted in there are the 15 to 100 amps. So if you have a 15 to 100 amp breaker, they're all going to be the same size, but they're going to be classified by the largest. So that would be the 100 amp breaker size classification. So I could have a 15 amp breaker. It's going to be a 100 amp frame size. I've got the 250 to 400 amp bullet point highlighted. So if I have a 250 amp breaker and a 400 amp breaker, they're going to be the same size. They're going to be that 400 amp classification. But any breaker in that size between 250 and 400 is all going to be in that same frame size. Moving on to 220, circuit breaker types and ratings. I've got table 1 highlighted on page 5. You're going to have the question come out of that table 1 with the molded case circuit breakers ratings recognized by UL. So they're going to have different ratings for AC current, or AC or DC. You're going to have a question come out of that. Current rating 221. The first paragraph, last sentence of 221 is highlighted. The ampere rating on the circuit breaker is located on the handle of the device. Circuit breaker, this square D type circuit breaker, 20 amp circuit breaker listed on the handle of the device. Pretty much seen that on every type of circuit breaker I've seen. That can get worn off over time if it's a breaker somebody's trying to use as a switch. It can get wiped off, but it's usually always right there. So highlight that and then highlight. I got the little handle on there highlighted where it shows the rating. Interrupting capacity rating 222. So this is important. I don't usually tell y'all to read all of this stuff, but in order to understand interrupting capacity, this is like the description they give of a dam and a river is a good job of explaining interrupting capacity that I'm not going to go into. But I think they do a good job of explaining that in these few pages. So I would recommend reading this section to have a better understanding of this interrupting capacity rating. But it's just the amount of current that something can actually separate. Because when electricity is flowing through things, it creates a magnetic field and stuff. If you have so much current, stuff's going to want to stick together and you're not going to have the force to pull it apart. The highlight that I have in this is on page 7, that split paragraph between page 6 and page 7. The last sentence is highlighted. That's on page 7. Therefore, selecting overcurrent protected device with the proper interrupting capacity is extremely important in all electrical systems. Very important to select a breaker or fuse with the correct interrupting capacity. Flipping over to page 8, still in this same section, I've got the starts on the last paragraph on page 8. It starts with the second sentence and then finishes on page 9. So I got the breaker interrupting. This is an online test question. The breaker interrupting capacity is based on tests to which the breaker is subjected. There are 2 such tests. One is set up by the Underwriters Laboratories, or UL, Inc., and the other by the National Electrical Manufacturers Association, or NEMA. So UL and NEMA set up these test what the interrupting rating of the breakers or fuses or you have heard of both of those so far. I think that's all the way back in electrical 1. So you should have heard that. But you've heard that before. Second paragraph on page 9, right there in the middle of the paragraph, I've got to highlight. If the breaker were rated at 600 volts, it would be required to trip within 70 seconds at 300% of the rated current. So it's just going through how fast certain circuit breakers are going to trip. Next paragraph down, first sentence is highlighted. The interrupting capacity of a circuit breaker is based on its rated voltage. So different breakers are rated at different voltages. Simple enough. I've got a couple more highlights that come out of those bullet points. So there's different categories of interrupting capacity. They have the standard interrupting capacity, the high interrupting capacity, and current limiting. And then details are listed in the 3 bullet points. In the first bullet point, I've got the sentence that splits the columns, still on page 9 highlighted. In residential applications, the available fault current is seldom higher than 10,000 amps or even near this. We don't get to 10,000 amps at our houses. It can be scary if we do. Second bullet point is the high interrupting capacity circuit breakers. I've got the second sentence in that bullet point highlighted. The FH type circuit breaker has an interrupting capacity of 65,000 amps. Symmetrical at 240 volts AC. That is a ton of interrupting capacity. Page 10, a lot of highlights on page 10. First paragraph, first 2 sentences are highlighted on page 10. There are circuit breakers available for almost every need in any electrical system. For example, in circuits where the circuit breaker must be highly sensitive to amperage changes, in an environment where the temperature changes are great, the ambient compensating circuit breaker may be used. So that's temperature changes a lot with electricity. So you can have a circuit breaker that makes changes based on the temperature, because at certain temperatures they should trip sooner or later than others. Third paragraph on page 10, first sentence is an online test question. At currents below a threshold of about 1,000 amps, the current limiting circuit breaker performs in a manner similar to a conventional thermomagnetic circuit breaker. That's a regular circuit breaker, just like a regular circuit breaker, kind of like you'd see. I guess kind of a circuit breaker you see on the bottom right there, or on the right side of page 11. The next paragraph, first sentence, is another online test question. For a 100 amp frame, current limiting circuit breakers, the threshold of current limitations occur in the range of 1,000 to 2,000 amps. Moving on from there, nothing else highlighted on page 10 or page 11. Flipping over to page 12. Moving on to ground fault circuit interrupters, GFCIs. We need to know what GFCI stands for. Just personally, I always get the C messed up. I always think it's circuit interrupter or current interrupter, kind of the same thing, but not really. But ground fault circuit interrupters, GFCIs. Flip it over to page 12. They go through bullet points of the effects of electricity on the body, and that last bullet point of the first set of bullet points on page 12 is highlighted. Over 200 milliamps will create severe burns and muscle contractions. The heart is more likely to stop than fibrillate. So that over 200 milliamps, that's bad. Your heart is more likely to stop than fibrillate. Skip a paragraph, and I've got that whole next paragraph highlighted. Ground fault circuit interrupters, GFCIs, are Class A protected devices built in accordance with UL standards for ground fault circuit interrupters. UL defines a Class A device as one that will trip when a fault current to ground is 6 milliamps or more. Also, Class A devices must not trip over 4. That means they're going to trip between 4 and 6 milliamps. That's very low, and they trip very fast. GFCIs there's no telling how many lives GFCIs have saved over the last 30 years that they've been required in most houses. Right-hand side of the page, the paragraph that's right after the bullet point, second to last paragraph on page 12. Whole thing is highlighted as an online test question. There are two types of GFCI receptacles. The feed-through type will provide GFCI protection to the remainder of the outlets in the circuit, similar to the GFCI circuit breaker. The second one, a non-feed-through type, offers protection only at the point of installation. Both types are available in various styles. Most all GFCIs are gonna have are going to be the feed-through type. You can buy the non-feed-through type for a little bit cheaper, but most of the time you're getting those feed-through type GFCIs. It's very important how you wire up GFCIs. You have a line side and a load side. Most of the time I've seen people trying to wire this stuff up. You just have to know what side your hot's coming, or your line side is coming from, and then if you're doing the feed-through type, where that stuff is going. It's very important. If you don't get those right, they don't work right. That's all for section 2. So last section of this chapter is section 3, sizing and selecting fuses. You're going to have 3 different types of fuses. The dual element fuse, Edison-based fuse, and the non-renewable fuse. Fuse types and markings. Where you see in the second bullet point, where you see the dual element fuse, I've got that sentence highlighted. A typical example is the motor circuit. A dual element fuse is generally permitted to be sized up to 175% of the non-time delay fuse and up to 300% of the motor full load amperes. Moving on from there, plug fuses, 311. 311 on page 16. I've got about the second half of that first paragraph highlighted. Edison-based fuses are permitted only as replacements in existing installations. All new work must include type S fuses in accordance with NEC, which states that the plug fuses of Edison type may be used only as replacements in existing installations where there is no evidence of overfusing or tampering. This is old stuff. Seen these in old houses. I've replaced these panel boxes. This is older stuff that you're not putting new versions of this still in. You can only replace fuses where they already are. Next paragraph, again, about the second half of that paragraph is highlighted right after where you see the 0 to 30 amps right in the middle of the paragraph. Each type S fuse has a base of a different size and matching adapter. Once an adapter is screwed into a standard Edison-based fuse holder, it locks in place and is not readily removed without destroying the fuse holder. As a result, only type S fuses with a size the same as that of the adapter may be inserted. 2 types of plug fuses are shown in figure 11, and S adapter is also shown. So that's the 3 pictures on there. You can see that S fuse adapter base, and then the type S fuse. That's just saying those lock into place, and you can't get them out. Next paragraph, the whole thing's highlighted. Plug fuses are also made in time delay types that permit a longer period of overload flow for a longer period of overload flow before operation, such as a motor inrush current and other higher than normal currents. They are available in ratings up to 30 amps in both Edison-based and type S. Not used that much. I've seen them a little bit, but they're going to be, I would guess, in the next 20-ish years, those are going to go, there's not going to be a whole lot of those left. Cartridge fuses, 312. So these are normally what you think of whenever you think of a fuse, or at least I do. 312 cartridge fuses. Second sentence through the end of the paragraph are highlighted. Older cartridge fuses were provided with a means to renew the fuse by unscrewing the end cap and replacing links. These fuses presented safety hazards because it was easy to tamper with them to override the safety feature. Their production has been discontinued. I've never seen one of these. These are older than what I've seen. I've never seen a fuse you can take apart and replace the connection. Other than they're not really, they're just connection links. It's kind of how they do linemen and stuff like that, or can take the center of those whenever they turn on power at a pole or something like that. Those are kind of like that, but no fuses you guys are going to see are going to have replacement links. Flipping over to page 18. First full paragraph on page 18, first sentence is an online test question. Single element fuses have a very high speed of response to overcurrents. That's why fuses, a lot of times fuses are picked in lieu of a circuit breaker, just because they can act faster, cheaper, stuff like that. Next paragraph, first sentence is highlighted. Dual element cartridge fuses. I highly recommend looking up videos. I think it's Eaton that does a pretty good video of a dual element cartridge fuse. Unlike single element fuses, the dual element fuse can be applied in circuits subject to temporary motor overload and surge currents to provide both high performance short circuit and overload protection. Skip a sentence, and I've got the rest of the paragraph highlighted as an online test, or not online test question, but separate question. The dual element fuse contains two distinct types of elements. Electrically, the two elements are connected in series. The fuse links, similar to those used in a single element fuse, perform the short circuit protection function. The overload element provides protection against low level overcurrents or overloads that will hold an overload that is 5 times greater than the ampere rating of the fuse for a minimum of time of 10 seconds. So it's good to, I wish they don't show a good picture of the inside of these. But again, that Eaton video, I think it's Eaton, shows a good, does a good job of showing the insides of a dual element fuse. Fuse classes and markings, 313, second paragraph is highlighted. NEC section 240.60C requires that any cartridge fuses used for both branch circuit or feeder protection must be plainly marked, either by printing on the fuse barrel or by a label attached to the barrel showing the following. Then I've got the voltage rating, but it's important to know that all of those are highlighted. You can notice the interrupting rating if other than 10,000 amps. So fuses have to be able to have an interrupting rating of 10,000 amps. If it doesn't have a rating, it's assumed it's 10,000. If it's other than 10,000, it has to be listed or labeled on there. Going into sizing fuses, 320. Sizing fuses, nothing highlighted in a dual element time delay fuse, but those are used a ton. I would highly recommend reading through that. Non-time delay fuses, flipping over to page 20. They're going through the different non-time delay fuses or applications thereof. The first bullet point on page 20 is highlighted to go along with that section, branch circuit with no motor loads. So the fuse size must be at least 125% of the continuous load plus 100% of the non-continuous load. That's for non-time delay fuses. The next paragraph, or the first full paragraph on page 20 is highlighted. When sizing fuses for a given application, a schematic drawing of the system will help tremendously. Such drawings do not have to be detailed. A single line schematic will suffice. That's one to look at, such as the one shown in figure 13 or up on the board. So that shows you want your stuff coordinated, which is what we're going into next. 330 coordination of overcurrent protective devices. Page 21, 330, first sentence is highlighted. Coordination is the name given to the time current relationship among a number of overcurrent devices connected in series, such as fuses in a main feeder, sub-feeder, or branch circuits. My last highlight is on the right-hand side of page 21, that second paragraph of this section. Selective coordination is the selection of overcurrent devices with a time current characteristics that ensure the clearing of fault or short circuit by the device nearest the fault on the line side of the fault. So what that means is I've got all my loads down here. My transformer transforming the power from one thing to another is up here. And then I've got my disconnecting means, circuit breaker, disconnecting device, electric meter, main circuit breaker, and then all my 20 amp circuit breakers. So I've got 20 amp circuit breakers here, a 200 amp breaker here, and then it's got a circuit breaker and a fuse here. So if I had one of these loads get overloaded, one of these 20 amp loads, I don't want this circuit breaker or this fuse popping because it's going to shut down everything. Same thing here, like same thing at your house. Say these were 20 amp circuit breakers at your house and you got a 200 amp main. This could be like for like your house. So you don't want Joe Schmo, or you don't want your kids hooking up 5 toasters and a hairdryer on one 20 amp load and your whole house to trip out. You want that one circuit breaker to trip out. That's what coordination is. That's making sure that your stuff is in line so that the stuff trips in closest to the load and it's not going to affect other stuff in the same system. So that's what coordination is. That's all I've got for this chapter. You've got the section reviews, module review, little short module review on page 24, and supplemental exercise on page 25. And then your quiz is ready to go on Canvas.